All right, I'm gonna go ahead and start working on these, y'all. Um, today we're gonna continue with where we left off. So not yesterday, sorry, Wednesday, we were looking at some different rules of derivatives, right? We started off with how to handle the power rule, how to deal with constants when we do derivatives. I mixed in what they call the sum and difference rules, but I made sure to connect that back to how we did it with limits, right? So when it comes dealing with sum and difference, that's where you can do the derivative of individual terms. So I didn't directly say that, but that was something we learned from limits and we brought over. Two things though that we have to be watchful for are going to be the product rule and the quotient rule. Okay, both those are special rules that we have to make sure to use. And today we're going to introduce the chain rule, which is going to be another one that will definitely come up a lot when you're dealing with derivatives. Okay, you won't always have a product, you won't always have a quotient, but you should always watch for a chain rule. Okay, with that said here, are we good if I go back to what we did yesterday for these two? Is there any concerns here? Or are we good with that? I think that if I recall correctly, that's the same two functions we did yesterday, right? So where does the 1/2 come from? Just make sure for anybody who needs to remind the reminder. That's the square root, right? So a square root is a positive 1/2, right? We bring that positive 1/2 down here in front, and then we subtract one, which is why it's now negative 1/2. Just be careful to see here. The reason this is negative is because it was subtraction. Okay. Over here, the derivative of quadratic. Okay. Now, as far as dealing with my two functions, okay, we're going to be dividing them. So that means what they're wanting us to do is to say, hey, this is the function we're looking at now, and I need to go take the derivative of that. Once we get into using some division, this is where we have to go back and say, hey, this is a quotient rule now. Combination and composite definition of functions, though, as you see here, just kind of reminds you, it's like, hey, this is its own function now. But each of these can be looked at as an individual function within that. Okay, so that's why here it's like, okay, remember to do them separately. They are individual things that we can look at. But the quotient rule says that, hey, when I go over here to do the derivative of beta of x, I need to do low d high minus high d low all over low squared. All right. So I'm going to take whatever was in the denominator. So that'll be x squared plus 5. And I'm going to multiply it with the derivative of the part that's in the numerator. So low d high, and we found just now for the numerator, it's negative 1/2 x to the negative 1/2. And then what do we do next? All right. So this is where it's minus sign is the key though, right? Make sure, remember the product rule we added, but quotient rule we need to subtract. So it's low d high minus high d low. So we're going to put 3 minus the square root of x first, and then that's going to be multiplied with 2x. But that's all over low squared. Now, what do I have down here when I write it like this? What does that represent? That is the derivative, all right? What do we need to do from here? Simplify, right? But understand that is the derivative. Okay, we have found the derivative. All we need to do now is simplify. Really, the only thing I would say here that focus on is just do the distribution that these two terms need us to do. Okay, if you can combine like terms, yeah, go ahead and do that. But the distribution is really just the focus that we want to do. Okay, do not multiply this out unless it helps you in some way. Are we clear on that? Now, things you'll find is if you had like a polynomial function in the numerator and the denominator, sometimes you might be able to simplify by factoring something out and then dividing. So it may be that it works out nicer to not multiply it out in the long run. If we ever had to go deal with this from a graphing standpoint, not having it multiplied out helps us get to restrictions a little bit quicker, right? So that's why typically it's better just to leave the denominator alone. All we need to do is simplify the numerator. Is there any question though where I'm getting this from before we go into simplifying? Well, the final answer is we want to simplify. The denominator, yeah, keep it like that. That's correct. If you multiply it out, it's not wrong. That's just extra work you didn't have to do. Now make sure you see here, if you have 2 minus a half, that's going to give us 3 halves. Over here, we're not only going to distribute a 2x, but make sure you see again, we need to change the signs as we do this because we're subtracting. So the first term here, 2 times 3 is 6, but I'm going to put minus 6x. All right. But this time I'm going to put plus 2x to the 3 halves. All right. Now that one may not be as obvious, but remember, whenever you have a square root of x, you could have just wrote x to the 1/2 there as well. So 1 plus a half, well, that's 3 halves. That's where I'm getting this from, is when I do this multiplication, it gives me this. Just make sure again to see that as I distribute it, the reason I changed the signs is because we're subtracting, so I'm distributing that at the same time. Okay. Hopefully what you'll see here is, hey, we can end up combining like terms. Not always going to happen, but with this one, we can definitely combine like terms. So we'll get negative 5 halves, x to the negative 1/2, minus 6x plus 3 halves, x to the 3 halves. All right. That's just the numerator though, right? So remember, this is all over x squared plus 5 squared. So if we want to, we say now, hey, beta prime of x equals this all over x squared plus 5 squared. Okay. Now the part that gets really messy about this, I have fractions in the numerator. And anytime you have a negative exponent, that itself is a fraction. So technically we should be getting rid of that if we could. Okay. I don't want to spend time going through that whole process, but make sure you see here to get rid of that, I would need to multiply this fraction by 2 times x to the 1/2 on top and bottom. In the denominator, you could just put something like 2 squared of x in front of it and just leave that alone again, okay? But in the numerator, you need to distribute this to all 3 terms. And what that'll do is it'll get rid of those halves that we have in front as coefficients because of 2. Just make sure you see that the 6 needs to be multiplied by 2 as well. Multiplying by x to the 1/2 will take care of that negative 1/2 exponent at the very front. But make sure you see it impacts the other 2 as well. Okay. Any questions though with getting to this piece here? That's definitely one thing we need to be comfortable with. Any questions or concerns with the quotient rule that we jumped right into today? All right, is every function going to look like this though? No, right? Remember, I picked the one with the square root, so we're practicing our rational exponents as much as we can, okay? That's not going to be every function we look at. Please keep that in mind, okay? With that said, when you go back in your notes, make sure you see that yesterday we looked at Wednesday, we looked at the perspective of the product rule with these 2 functions. Here we looked at the quotient of those 2 functions and how it affects the quotient rule. Today, we got to jump into something that deals with kind of what we call composite functions. All right, so what you'll see here with this example, I have h of x equal to 2x cubed minus 1, but that whole thing is being squared. So how do we handle this when we want to take a derivative? What we're going to work towards is what we call the chain rule. Now, as you finish writing this down, though, what's something we can do to this function, though, to get it into the form where I can just look at terms rather than have to worry about the square? We can multiply it out, right? Now, if you want to, you can do a product rule here. Just make sure you see you have to write it twice to do the product rule. Nothing's wrong with that. I'm going to go ahead and FOIL this out though, so we can review just the sum and difference and power rules. So this will give us what? 4x to the sixth minus 4x cubed plus 1. Remember, as far as the derivative is concerned, you could have used the two factors and did the product rule. Or you can simplify this and then differentiate. Okay. Are we good though with where I'm getting that trinomial from? All right. So then here, hey, I want the derivative of this. So h prime of x is going to equal the derivative of this trinomial expression we found. The nice thing about it is, hey, that's just power rule in a constant term now. Okay. I remember as we were talking about, I think it was Monday, if you need to write d dx with each term so you can better visualize that, please feel free to do that. Nothing is wrong with that. Okay. What you do definitely need to be able to do here, though, is say, hey, I'm taking this one term at a time. Since I have addition and subtraction between them, I'm just going to do one term at a time. There's no multiplication as far as dealing with factors is concerned, and there's no division as far as fractions are concerned. This is a constant multiple when we look at this multiplication that gets tucked outside. Okay, that's the exception there. With that said, are we good if I put 24x to the fifth first? Where'd the 24 come from, y'all? My exponent was 6, right? For the derivative, I bring it down. 6 times 4, 24. Okay. Just be careful. Always watch that you subtract your exponent by 1. Okay. Next would be minus 12x squared. All right. Bring the 3 down, multiply it with the 4. What do I put? Huh?
Minus 12.
Minus 12x squared. Yeah. What do I put next?
Nothing.
Why not?
Because
And 0, right? It's a constant term. Again, that'd be a situation. If you need to see the plus 0 because that helps you, put plus 0. But we're done because the derivative of the constant is 0. Okay. So what do we have at that point once I get here? That is the derivative, right? And it's actually fully simplified this way. I'm good to go. So by doing our simplification first, right, my answer was already simplified too. This would be a good problem though, to go back and practice the product rule to see, make sure you do get the same thing. Okay. Now, what we want to jump into though and show is that, hey, there's another way to handle this by looking at it from the perspective of a composite function. What do I mean by that? Well, let's say f of x equals 2x cubed minus 1. That means then I could rewrite h of x as h of x equal to f of x squared. All right. That's the idea of a composite function, plugging one function into another. Okay. Well, let's look at it from that perspective. And I mixed up my slide. Sorry. So as we look at this slide here, this gives us what we call the chain rule. One thing that I want to be clear of is this is an operator from college algebra that we do want to be familiar with. Okay. That's going to be our composite operator. So f of g of x is how we look at that. So remember, all that means is you're taking g of x and plugging it into f of x. So I know that's not what we were doing here, but make sure you see, like, if I call it f of x, this is another way to write it. Okay. Technically, I should have wrote it like this. I'm sorry. Another way to kind of look at it is from that perspective. Okay. With that said, though, we can differentiate this without having to do all that simplifying. What happens is you'll see here, we can treat this as like it's x squared. Okay. That's where this comes from. I bring down the exponent and I subtract by 1. So this 2 is coming from that exponent here. And then 2 minus 1 is where this comes from. But the chain rule says you don't stop there because we have more inside. Well, guess what? That's where this comes in. All right, what you'll see here is the 2 times the derivative of the inside would give you 12x squared, and when you distribute it, hey, that's what we had before. All right, and this is what we call the chain rule. Like, hey, I'm going to do the derivative of what's on the outside. Once I finish that derivative, I then do the derivative of what's on the inside. Now, what I hope you see here is the main thing is that going through this process, we should still get the same thing as what we just saw. Okay. Everyone got this before we do an example? Everyone else is good? All right, so here's one that we can definitely use a chain rule on. Now, the way I have it written here, what way stands out first and foremost? Y'all, I wrote that wrong. Give me 1 second. That's what it's supposed to be. Didn't copy. Make sure you put the square on the X. I did make an adjustment. But the way it's written right now, what rule is someone wanting to go to first? The division, right? How can we rewrite this so we don't have to use the quotient rule since it's just a 3 in the numerator? That was one of the things I want to make sure to point out here. There's nothing wrong with the quotient rule, but sometimes that can take a little bit longer than say, hey, if I just use a chain rule, okay? What I hope that you see here is I can rewrite this using what type of exponent? A negative exponent. By using that negative exponent, now I don't even have to bother with the chain rule. Now, if it was, say, like x plus 3 in the numerator, we would still have to do a product rule. But since it was just 3 in the numerator, hey, all I have to do here then is a chain rule for this problem. If you want to use the quotient rule, though, feel free to use the quotient rule. Nothing wrong with that. This will just save a couple steps. That's all. With that said, though, make sure you see here when I go do the derivative, then if I use this perspective, I'm saying, hey, what's the derivative of this 3 times x squared minus 2, all raised to the negative 3 as an exponent? Okay. Remember that 3 is just a constant multiple. So technically, I could just move that out front. Because it's a constant multiple. Which is why it's nice to kind of look at this from a negative exponent perspective. Okay. With that said, then, when I go to differentiate this, should be j prime of xr. I'm going to get 3 times negative 3. Where am I getting the negative 3 from? That was the exponent we had, right? I'm going to keep the base as it was. I'm not changing anything about it. I'm writing that again. Okay. What's my new exponent, though?
1.
Not 1. We had negative 3. We take 1 from it, right? So take 1 from negative 3, we get negative 4. So remember there, like the 1 is like, hey, subtract 1. Okay. Which always be careful with negative exponents because the number gets smaller, right? But we're not done yet because the chain rule tells me, hey, I took care of the outside part, but now I have to take care of the inside part of this function. So what I'm going to multiply by now is the derivative of the x squared minus 2. Which would end up being just 2x, right? So when we do that, we'll have j prime of x equals negative 9 times x squared minus 2 to the negative 4 times 2x, which we could write as negative 18x times x squared minus 2 to the negative 4 as an exponent. The chain rule is one of those ones that can it can be easily accidentally overlooked sometimes, so we have to be careful to watch for it, okay? And make sure you put a little star next to this one too, though, is kind of a way, how can I approach problems sometimes and change something from the beginning to where instead of having to do one method, I can do another, okay? So here's an example where, hey, I could have done the quotient rule. It wouldn't have been too bad because you still would have had to do a chain rule and the derivative of 3 is 0, so it's not horrible. But I didn't even have to write a fraction by making it a negative exponent. There's still a fraction involved though, because remember, -4 means that would still be in the denominator. Okay, so make sure you see that. Well, that would be fully simplified, right? The only thing that technically you could do is rewrite it as such. -18x all over x squared minus 2 to the fourth, where the negative should technically be all the way out front. But from my perspective here, just be careful with the homework. The homework may not want negative exponents in it, so keep that in mind from a homework perspective for Pearson. For a test, though, I feel like this often will be fine. Okay. Now, if I said, hey, find the derivative and now graph it, then this will probably be helpful to remind you, oh, hey, it's a rational function still. Okay. But if I'm just telling you to differentiate, this is perfect. You multiplied everything together on the outside that needed to be multiplied together. Any questions or concerns here with this one? Now make sure you see the correction I made at the beginning. I wrote just j of x here, right? But we should be writing j prime of x to show that, hey, this isn't the original function anymore. This represents the derivative of that. Okay. Now a question, because we haven't looked at it in a while. What if I said go find j prime of 3? What would that represent? Don't actually plug it in, but what would that represent? So we can plug it in, right? I will get some kind of constant value, but what does that value represent? It's a rate of change, specifically an instantaneous rate of change, right? What is it the slope of? Huh? Not J. Well, okay. At that point, we can make that justification, right? I guess what a better way to say it is, what do we call the line that would have that slope at that point? A tangent line. That's probably a better way to ask the question. That's why I'm getting to understand, like, hey, it's instantaneous rate of change. I call it the slope of the tangent line at that point, right? So those are things to make sure to keep in mind. Okay. We're getting on to a lot of derivatives, but Monday we're gonna have a little worksheet to try to make sure we put some of it together that we looked at from the first test as well as what we're doing here, okay? Anything else though before we move forward with this one?
Why did we multiply -9 with the x? Unless,
Well, because it's all multiplication at that point, so we want to just simplify it together since this is being multiplied and that was multiplied. Through the commutative associative property, we can bring them together. That allows us to just have one thing out front rather than it being separate. If the exponent was positive one, right? If we didn't need an exponent anymore, right? Then we can go ahead and distribute it. Everyone else is good? All right, so here's another problem then. So as we look at this problem that you're writing down, make sure you see I went back to the same F and G we've been working with since Wednesday, okay? We looked at it from the perspective of the product rule. The first problem we just did was the quotient rule with these two functions, okay? Now we're gonna look at it from the perspective of what we call the chain rule. So with that said, make sure that as you see this composite operator, just remind yourself that means, hey, I'm gonna start with F on the outside. I'm gonna plug G of X on the inside. What it means, okay? Composites are definitely important things to make sure we're comfortable with though, because a lot of stuff that we do deals with taking one function and plugging it into another. Look at my setup here for just teaching class. I use my iPad, right, as one function just to write on and display it. Okay, that's one function. The adapters to get to the display is its own function, right? So there's certain inputs and outputs that have to take place in a proper way for that to happen. Okay. So whenever we deal with mathematical perspective of this, make sure, remember, hey, sometimes I'm going to have to plug in the result of one function into another function. It's going to happen. Okay. Now, with that said, are we okay if I write this as h of x equals 3 minus the square root of x squared plus 5? What operation did I put on the outside here?
F of X.
But the square root's on the outside, right? And x squared plus 5, I put inside the square root. That's how you know that, hey, f of x was on the outside and I went and plugged in g of x. Okay.
X from the outside, G of X from the inside.
Mhm. Now, keep in mind, we could always do it the other direction, right? If we wanted to, you could always say, hey, there might be a situation where I need to do 3 minus the square root of x squared plus 5. That's another function out there, but that would just be g of f of x. Okay, so always pay attention that sometimes we might need different perspectives. But for our case, I wanted to do the radical on the outside. Okay. Now, with that said, things to make sure to remember as we deal with this, we've kind of looked at the derivative of these things already. Okay. So specifically right now, don't forget that the derivative of g of x was just 2x. I'm not going to put f of x right now because it's going to look a little different. But when I go take the derivative of this, what is the derivative of 3 itself? 0. So I don't need that, right? But this is where having this written in that rational exponent becomes helpful, right? Because the overall idea of what we did before stays the same. We're going to say, hey, this is going to equal negative 1/2. So we're dropping this in front of the negative sign. But what should my new exponent be when I subtract 1? Right, so here we're doing 1/2 minus 1, which will give us that negative 1/2 we had before. Okay. Are we done there or something else? Why do we have to multiply by something else? Right, the chain rule, right? Because we had something inside the square root that wasn't just x, right? Technically, we do the chain rule all the time, just so you know. If you go back to this piece here and you look at just that, if we apply the chain rule to this, it would be 1/2 times x to the 1/2 times the derivative of x. But what is the derivative of x, y'all? It's just 1. So that's why we don't talk about the chain rule until now, because a lot of times we're just dealing with x by itself, so that would give us 1. Everyone follow me on that? So make sure you see here, though, this is this problem. Now that it's x squared plus 5, I definitely need to make sure I remind myself, hey, don't forget the inside of my function. That's where this derivative is going to go into place. Now, as mentioned, that was the one we've been working with. So it's going to be just 2x. What should I multiply the 2x with, though, to finish simplifying? The 2x is not negative, no. That negative here is still in front.
Would be negative X.
It would be just negative x. Where'd your fraction go? Make sure you see you had 2 times 1/2, right? So that's gone. Just make sure I put my negative x in front. Okay. Another great way to write this one is to say, hey, when I'm done with this, it's going to be negative x all over the square root of our x squared plus 5. No, but just know that this would be to me a problem where, hey, it's just the square root, making sure we know it's a square root is helpful. Okay, that's why I rewrite it right now. Don't forget that 1/2 is a square root. Don't forget negative means the denominator. Okay. But as I mentioned, like on the test, if you stopped at negative x times the x squared plus 5, that quantity raised to negative 1/2, I'd be fine. Okay. The homework, though, is more than likely going to make you put it in like what I wrote there at the very bottom. Thankfully, not as much simplifying as we saw before, right? But definitely be careful to see like, hey, that 2x, I can multiply that with something. Any questions I clear for somebody there?
Negative half minus one. Should be like 1.5.
Like if you did it again, you're saying? Yeah, so if you do negative 1/2 and we did another derivative and subtract one, it'd be, I would just typically write, that's where we're getting that 3/2 from. Like 1 plus a half or 2 minus a half. Whenever you're dealing with exponents, don't ever use mixed numbers. Okay. That'd be one thing, like, it's fine to think of it as a mixed number, right? With some of the stuff we're doing, but make sure we're using improper fractions. Okay. Now, we only have a couple of minutes left, but there is one thing I want to make sure that we're clear on as far as like what's expected with dealing with something. What you're gonna see is as you start seeing some of the application problems, paying attention to what they're asking for is going to matter a lot. Okay, so as I mentioned on the test, I gave y'all a bonus problem that asked you for the rate of change of the profit. Well, to get the profit, and you have a cost and a revenue function, we first have to remember that profit is revenue minus the cost. That's definitely one thing you have to make sure you remember, is that if you're ever looking for a profit function, that is going to be your revenue minus the cost. Oops. Okay. You're going to find that a lot of times they're not going to give you a profit function. They're going to make you go get by subtracting. Sometimes they will, sometimes they won't. I shouldn't say that all the time, but just expect to have to do it yourself. What you're going to find is, though, as you can see here, they like to throw different words there. So this one, they're bringing an average cost, and you're going to see the other one's going to be average revenue. And even if they don't put this here as far as kind of a title on the problem, reading it is going to be very important, because when I get through this problem, they want us to find the rate of change of the average cost. Find the rate at which the average cost is changing. But what do they give us here? That's the cost function. Does everyone understand that? Now, understand average cost is, you'll see here, what do you do to get average of any of them? Divide by X, right? Think about an average though. There's what, 2, 4, 6, 8, 9, 10 of us in here right now. If we wanted the average height, we would sum up everyone's height and divide by how many people in the room, right? That's where the idea of average cost is coming from. If you make 20 different things, what are they talking about? Hot sauce here. If you make 20 bottles of hot sauce and you say, hey, this is how much it costs to make those 20, you just divide by 20 to determine how much each bottle costs individually, right? That's why we like an average cost. How much is it costing per bottle to make that? So if I look at this problem here, if I plug 81 into this cost function, it's going to give me the cost to make 81 bottles, right? But if I go and do this, then what we get back from this is no longer going to be the cost per bottle. I mean, the total cost of making 81 bottles, but this will be the cost per bottle made for whatever number we want. So this is kind of nice because you can have this function from the beginning, and you could just say, hey, I'm interested in how can I minimize the cost per bottle. All right. A lot of times it's just going to depend kind of on the conversation that you're trying to have, right? How are we trying to discuss, or what perspective are we trying to use to look at something? And that's what's going to kind of determine, should I use the cost function, the average cost function? And you're going to find there's going to be different terms that we add to this course itself, right? Have any of you been taking business classes yet? So I'm sure some of you've already seen that terminology is really important so that you use the correct perspective, okay? Now, what should we do with this is the question, right? So this is telling us to find the rate at which it's changing, right? So what do I need to actually find? Derivative, right? Is everyone clear with that? Now, if I just say A sub C of X here, just kind of simplify, we'll say A because we're dealing with the average. I'm putting the C there because of cost. Know that we're trying to find the derivative of that function. What are some ways you can find the derivative of this? You do the quotient rule, right? Do we have to do the quotient rule though? Right? Couldn't we break it down into two separate terms though? Couldn't we do that? At that point, what I would do is just say, start using your negative exponents, right? And you can use the power rule. So this would be a situation. I know, like I said, we don't have full time to do both problems. My thing was to pay attention to what it's asking for, to make sure to introduce this piece here. Everyone follow me on that? Well, hopefully what you'll see here, you could have just jumped straight into the quotient rule to find that derivative if you wanted to, okay? And as time permits on next week, I'll make sure we do some of these so it's not just introducing, okay? But also know, as we've looked at with some other problems, hey, I can go break this into two separate terms, make things have negative exponents, right? Specifically, when you look at this one here, it'd be 375 x to the negative 1 plus 0.75 x to the negative 1/4. And then I just have to use the power rule to complete this, okay, on those two terms. So that's definitely something you want to look at. With that said, when we talk about simplifying, we can leave negative exponents because guess what? Our calculator, if you have the TI-30, that is, you could just stick negative exponents in it. You don't have to worry about that, okay? Okay with that brief intro? Make sure you see here, like I had two examples, but this other one would just be R of X over X, okay? What you'll see here, though, is what company's on both of them. Tongue tied, right? It's both of them the same thing, right? So the next step would be like, hey, let's go do the profit because now we have the cost and the revenue, we can bring them together to get the profit. Okay. Any concern though with what average cost, average revenue, average profit means? We're all good why we're dividing by X though? Okay. Well, that's all we have time for today. So I'll make sure, like I said, we look at that and we'll definitely look at the chain rule some more.